So good morning everybody. So today we shall continue our discussion on distributed temperature sensor. So the temperature is mapped in terms of change in absorption or scattering. So scattering essentially means there are the backscatter component will vary with respect to temperature because of the local deformation of the optical fiber. And also generally if the temperature becomes high and there are doped ions, the excited state of those doped ions like rare earth doping, erbium or neodymium, so those states will vary, so that way the scattering component will also vary. So to localize the point of measurement, this is similar to the ultrasound ranging principle that we had discussed while discussion on piezoelectric sensor. Only thing here we will do it with light, that is a laser, and this laser is usually a pulsed laser diode. Depending on the requirement of the uh, wavelength, the wavelength of the laser diode are chosen, and depending on the doping of the optical fiber. Of course, there are other solid state lasers are also used for some other scattering type. There could be three kind of scattering those may be present in optical fiber. One is that normal Rayleigh scattering, and another is Brillouin scattering, and another is Raman scattering. So Rayleigh scattering basically is available for all power of the light, but generally Brillouin scattering is medium power, and for Raman scattering we may require high power laser pulse. Usually the laser is inbuilt in that in the circuit itself, and from that the fiber adapter comes out. Generally these kind of instruments are portable instrument and used for field measurement also, so therefore construction wise they are made very rugged. This is an optical isolator. So optical isolator means this will block the light which will be coming in the return path. So if there are some backscatter component which may come here, so at that place it will block. Now this is the sensing fiber. And then we have a directional coupler here. And then we have a fast response photodiode. It could be an APD. And then there could be signal processing unit. Usually the pulse is triggered from this signal processing unit. Through a laser driver. Now typically the resolution of the space depends on the pulse width, because what is happening that we are launching a pulse here and then measuring the backscattered component. So therefore the resolution will depend on the pulse width and the range will depend on the repetition rate. That is the distance that will be covered will depend on this. Suppose this could be 1 millisecond and this could be 0.1 nanosecond or maybe 10-20 picosecond or so. So this is the sensing fiber. Sensing fiber is usually armored in a cable and with thermally conductive cable, such that the temperature, outside temperature is transported to the fiber. However, the temperature induced deformation should not make it brittle. So therefore, some kind of coating is put on top of this sensing fiber and then it is put inside the cable. So the cable is a metal cable and the backscattered component or its absorption vary with temperature. So that is coded in terms of the space. So now, after launching the first pulse, so there will be a subsequent amount of time, like 0.1 nanosecond of time will be used to integrate the backscattered energy. So that means this during this period, this 1 millisecond period, basically we will be measuring the backscattered energy every 0.1 nanosecond. So that means there could be a gating pulse. If I define it in, say, continuous time, so that will be, there will be that say detector output will be IDT, and then there will be a getting signal, and this will be integrated over the time period of capital T, that is 0.1 nanosecond here. And then after that it will give the output. It may, of course, general in practical situation, whatever, that the backscattered component no longer uh, supported by 0.1 nanosecond, there will be sprayed because of the dispersion of the optical fiber. So therefore, usually this another 0.1 nanosecond, or often it is integrated up to twice of this time period to get that energy, and then the that would be integrated. So that gives the output captured via a getting signal. GT. And this is the photo detector output. So this is the final output here. Now this time, which would be counted in integer multiple of that 0.1 nanosecond. The same trigger generator also generate the phase trigger signal to the counter to shift this getting pulse. So these are the backscattered component. So those are coming, of course, continuous in time as the pulse propagates. But to capture corresponding to a pulse energy, input energy, how much is the backscattered energy? So that need to be seen. Now, if this is say 1 millisecond, is the next pulse that has been launched. So therefore, the full during this 1 millisecond duration, all such shifted pulse phase trigger will be generated, and that will be fed to the integrator. The transit time tau for a distance d is equal to dn by c. So the light will travel twice tau. So this distance is basically twice tau. If this is the distance and is the travel time, so this one is twice tau, because the resolution depends on the pulse width. Say if it is 0.1 nanosecond, so that will travel take 2 into d into 1.5 is approximate refractive index of the glass, and so d could be so if we have 100 picosecond pulse width or 0.1 nanosecond pulse width, we can achieve a resolution. The best resolution could be 1 centimeter. Usually, due to the floor noise, the resolution suffers, and though this gives a single measurement, due to noise that may not be, the discontinuities may not be very prominent. What is done is that after 1 millisecond, again one pulse will be there, and assuming that in 1 millisecond, 2 millisecond time, the uh, temperature of that spot may not change drastically, because thermal time constants are usually high. So therefore, we can make n number of such repeated measurements and correspondingly average the output. However, typically backscattered components are very noisy, and for reliable measurement, reliable mapping of temperature, a number of scans are taken and averaged. To reduce the noise floor. Now, The range depends on that 1 millisecond or whatever be it. If it is 1 millisecond, range of measurement depends on the pulse repetition rate. Say for 1 millisecond, D would be like 10 to the power 5 meter, or 100 kilometer. So therefore, we can have a very long range of measurement. Of course, in this case, from this measurement point of view, this is all right. However, so the number of measurement points that here it is 1 millisecond by that 0.1. So that means 100 kilometer by the 10 to the power minus 10 to the power 5 by 10 to the power minus 2. So that is 10 to the power 7. So therefore, basically, the counter that is generating that shifting, the shift here, which is shifting this pulse and correspondingly coding it in terms of the numbers in time or space. So that need to be very high. So typically that could be a 64-bit or 128-bit counter would be required. Now, OTDs are also popularly used for monitoring the discontinuity. So that is, of course, much easier. They are routinely used for monitoring discontinuity. And imperfect coupling. Of two optical fibers. So because in case of discontinuity, the reflection will be very high. So therefore that can be easily, that will be simply not the backscattered component, rather back reflected component. And that will give a very prominent high power peak compared to the kind of this peak given by the continuous backscattered component triggered by temperature variation. So
Hello.
therefore,
Excuse
yes,
me, sir. Sir, what is OTDR?
OTDR is optical time domain reflectometer. Where I have written it?
Thank you, sir.
I have written it somewhere. I have not written. Okay. Acha, here I have written. So OTDR is optical time domain reflectometer. Time domain reflectometry. So that is the principle. So that is about this distributed temperature sensor. Now there could be several variations of this method and little bit of complicated arrangements could be there, but this could be a simplest kind of arrangement where the temperature sensitivity will be 5 degree, 10 degree or so. For better sensitivity, usually instead of pulse laser diode, some high power pulse lasers are used where the sensitivity can be improved by increasing the pulse power. And also, if we do some kind of doping, then also the sensitivity uh, of the backscattered component increases. So, say for example, for neodymium ion doped fiber, percent change in absorption at 930 nanometer could be approximately 20% per 100 degrees Celsius. So therefore, that way the sensitivity could be improved if it is doped by certain ions. The other way is that we can launch a high power pulsed laser. The OFDR, that is the frequency domain reflectometry, is similar that we have discussed for the piezoelectric case also.
Hello.
Yes,
Excuse me, sir. Sir, actually, I had one question that when the heat is applied to the sensing arm, not only the length but the refractive index also changes.
yes,
So,
yes.
so for that, so how can we use a constant refractive index in our like calculations?
So that is an assumption, but because we are assuming that just 1 minute, what happened?
Sure.
I think now, right. So when the pulse is launched, there will be a continuous backscattered component. Okay.
Yes.
And then that will be, but when there is somewhere a temperature change is there in a zone, at this zone actually there will be a dip, or if we plot in a negative one in the relative sense, we can also put it as a gain.
So,
So,
sir, where the
so
temperature changes.
basically, if we see the trace, it will be like this. Continuously, the power is changing. Somewhere it will be like this and like that. It will be much more noisy usually if we look at the OTDR trace, the real OTDR.
Oh, okay, sir.
Okay, then we make lots of average, then we can get a smooth one. Then we can say that roughly there is a relative change here, and that relative change can be mapped to temperature. Okay,
Oh, thank you, sir.
so otherwise there will be what happens? There will be an exponential decay of the power. By that law is there.
Okay, sir. Thank you, sir.
And also that exponential backscattering could be due to the normal scattering. But if there is some change, so this is like time or space loss. We can make it in dB. This would be relative loss in dB. Now, in case of wave deer, only the localization technique vary, the sensing fiber, etc., and the sensing mechanism that may remain same. There are other kind of, here we have used the simplest sensing mechanism where one end is mirror is there, and so that can be used to also know that whether the fiber is intact or not, the where from we are getting the dominant reflection, so that way that from the end point if we get a dominant reflection we can know that all the fibers is intact. There are other kind of sensing mechanism that where we put a coil, so that means the path is rooted in a closed loop. So usually while installing the electrical wires, these fibers are uh, installed along with a armor cable with the electrical cable. Typically in buildings, modern buildings, most of the fire happens due to some kind of electrical malfunction. So therefore, these fibers are laid down where when that electrical cabling is done along with the power cable. There are of course some specialized power cables are also there where inside the cable the fiber is in the same armored cable we have that current carrying conductor and the optical fiber itself. So usually if we can do some kind of uh, continuous monitoring by observing the pattern. So in such cases, even say local sparking can be detected. Momentarily, there will be very high rate of change of uh, temperature. So that can also be captured because here the pulse width is quite small temporally. So therefore, it can also localize such kind of local and transient activities. In that case, of course, this trace has to be usually monitored continuously. So the OFDR is, of course, very much similar. The optical system is same. It could be a pulse, it could be a laser diode, which need to be modulated at a high frequency. Usually, for a high power pulse laser, there is a separate modulator is kept. Because high power pulse laser, though we can generate a switch, but to make a frequency modulation, it is difficult. So a separate frequency modulator is kept in high power pulse laser. But laser diode having say roughly 1 watt of power, so that can be directly modulated. Uh, so direct modulation, of course, is done generally with a DC part, with a AC part on top of a DC part. Because if I switch off the laser diode, then it takes some time to turn on. So instead of that, basically it is operated with some DC power, and then on top of that, the AC part is there. So we have a voltage control oscillator here, which is driving this one, and a driver, of course, would be there. This is driven by a ramp, and because we are doing in optical domain, so typically such kind of, and we want to get a good resolution in frequency. So this can be at a center frequency of 8 gigahertz or 10 gigahertz or 12 gigahertz or so, and then this is frequency modulated. Sorry. Something like this. It is the detector. So this will give, again we have feed this to a, this will give a bit frequency FB, which can be measured by an FFT analyzer, or again we can call it a signal processing unit. I think this ramp signal is here. So basically whatever the frequency is used to drive the laser diode through this driver, so that is fed to this multiplier, and also we are taking the photodetector output and being multiplied after some and preamplifier. So that will give rise to a shift frequency, because this light takes some time to travel this distance, and then it is then the backscattered component is getting detected by the photodetector. So therefore this point, whatever the signal, electrical signal is being used to drive the frequency of the VCO, this signal, that frequency, and this frequency will have a difference in frequency depending on the slope of this ramp. Typically, ramping rate could be in kilohertz, like say 50 kilohertz. So ramping time would be so if I use a shift of 1 megahertz, 10 to the power 6, 20 microsecond. AP, the bit frequency, again is a function of this time delay tau into delta F by Tm. That is the ramping time. A ramping period, delta F frequency deviation. Then, so for Tm equal to 20 microsecond, delta F FB say 1 megahertz, if it is FB is 1 megahertz, say FB 1 megahertz. Twenty into 10 to the power minus 6. So therefore D could be like 2000 meter would be the range. That corresponding to the ramping time. The resolution of course will depend on how finely a P can be measured. On the resolution bandwidth of the spectrum analyzer or the spectrum estimator. So typically if we take a range of 1 megahertz, easily we can resolve say 1 kilohertz or so. So then the resolution could be corresponding to 1 kilohertz. We can get whatever be the tau that we will, AP is 1 kilohertz. So delta F is 1 megahertz, and correspondingly we will get a tau. So that could be resolved. So 1 in 1000 that could be resolved. So that means 2 meter or so can be resolved. Can be available, can be 1 kilohertz or so. For a maximum analysis of 1 megahertz or 10 megahertz. So therefore we can get the resolution 1 in 1000 like 2 meters. Now advantage of this WaveDR is in better resolution. And disadvantage is that higher response time. And of course lower range. Typically wave tiers are of lower range than the compared to the OTTers, but the resolution is typically better because when we estimate the frequency, so that time lot of noise filtering is done. So unlike that OTDR. So here basically we are finding the frequency, not the amplitude of the energy of that reflected signal. So because here that energy of the reflected signal is important in case of OTDR, because finally here we have to put somewhere some threshold, okay, to know that what location it has appeared. So that give rise to the uncertainty. Now, in case of OFDR, the frequency appears in much more sharper manner. So that way the resolving power of OFDR is better. So generally that has been reported. Though of course it depends on the equipment and its performance. I think with that we will conclude that distributed discussion on distributed temperature sensor. We will not discuss the other techniques which are much more involved.